Our next, our next speaker is Zhuoran Yang. Zhuoran is a PhD candidate at Princeton. He's the VMware Research Fellow in the Reinforcement Learning Program. Zhuoran?
Hi, this talk is about exploration in policy gradient methods. And recently, there are many successes of policy gradient methods, such as AlphaGo and AlphaStar for solving the game of Go and StarCraft, respectively. These successes all require a gigantic amount of data, which make these methods unrealistic for problems where data acquisition is costly. So to achieve sample efficiency, we need to address the fundamental exploration and exploitation trade-off. So the goal of this work is to design a new policy optimization algorithm that is provably sample efficient. So our setting is the standard episodic MDP. The MDP consists of H time steps. At each time step, the agent observes the current state of the system and takes an action according to its policy, and then receives a reward and moves to the next state according to the Markov transition kernel. Here, the transition is unknown to us. And when the episode ends, the agent plays a brand new episode again and adjusts its policy. So the policy of the agent is a mapping from the current state to the distribution over actions, which specifies how the agent takes an action at each time step. And the goal is to learn the optimal policy which achieves the maximum value of the expected total return. So technically, the question is we want to address is how many episodes agents need to play so as to learn the optimal policy approximately. So next slide, please. So the algorithm we propose is an optimistic modification of the proximal policy optimization algorithm. It consists of two steps. First, we solve a policy evaluation problem by estimating the value function associated with the current policy. This is achieved by solving a least squares regression problem using all the historical data as the training data. And moreover, a key step is to add an additional bonus function to the solution of the least square problem so as to ensure that the obtained estimator is always an upper bound of the ground truth element-wise. Then based on the optimistic value function, we solve for the new policy by taking a mirror descent step, which corresponds to solving a KL divergence regularized problem, and the solution can be obtained in closed form. This algorithm is a general algorithm recipe in the sense that it can readily incorporate many functional approximation tools, such as kernel functions, linear functions, and neural networks, etc. And next slide, please. And finally, in terms of theory, we establish the sample complexity for achieving any epsilon accuracy, which is given by this upper bound. And here the DIM, the dimension, is the intrinsic dimension of the problem. So if our MDP can be embedded in a linear space, then this dimension is the dimensionality of the feature. If it's embedded in a kernel space, then this dimension is the effective dimension of the kernel space. And so this upper bound shows that our algorithm achieves sample efficiency provably. And that concludes my talk. Thank you.